Good night, everyone. So today is our week 5 lecture. I wish you are all doing well. So today we continue with the topic before. Last week we discussed op-amp, operational amplifier. So today we will continue with this topic. First, I will briefly introduce some more advanced topic called instrumentation amplifier. So the instrumentation amplifier is very important for this project. So like for analog signal conditioning. So for the weak biomedical signal, for example, ECG, EEG, and EMG, the first stage is amplification. So in order to amplify the signal and without influence, without distort the signal, we need to use very powerful amplification circuit. So this kind of circuit, you can use either op-amp, you can use one op-amp, two op-amp, or three op-amp. I will show you very soon to build the instrumentation amplifier. And then you can, based on the instrumentation amplifier, you can do the filtering. So today, if we have time, I also discuss about filter design. So this is very important for your assignment 2. I will discuss with the assignment 2 with you as well. Now we we go to the canvas. So every time we start from canvas. Actually, last week we discussed these slides. Mainly it's amplification. So we discussed so there's a very typical op-amp circuit. So basically, most important circuit is called the differential amplifier. So something is like this. We have input and output. We have positive input and negative input and output. So we want to measure the difference of these two ports. But this, I told you this one for the normal operational amplifier, you cannot directly use it because their gain is very big. So their gain is normally 10 power 5, so big again. If you have a signal to amplify like this, super high gain, and then will out of range. So normally they need to use negative feedback. So negative feedback to build the typical circuit. So one typical circuit called inverting amplifier. They discussed, I think discussed here. This is the inverting amplifier. Can you remember this circuit? And I will discuss with some not tutorial questions, some online voting question. So for this one, remember this one. So in input is negative, so the gain is minus RF over R1. So this is a very typical op-amp based inverting amplifier. So you need to.
Steve,
Hello?
sorry, are you sharing your screen? Because I don't see anything.
Oh, sorry. I forgot to share the screen. So you should. Sorry, my problem. I share the screen. I forgot. Yeah, this is my fault. Yeah. Yeah, sorry. I think this is the inverting amplifier. I'm discussing about very three typical amplification circuit. So the first one is called inverting amplifier. So you can see this inverting amplifier, how to remember it. So your input is from minus, is negative port, and also your gain, you need to remember, is minus RF over R1. So this is a negative feedback as well. So all the non-inverting amplifier, inverting amplifier, and also differential amplifier can be analyzed by using feedback. But don't worry, this one you no need to. If you cannot understand, it doesn't matter. But you just remember, for a normal amplifier, operation of the amplifier, you cannot directly use it. But you need to remember these three inverting amplifier, three amplifier circuit. So the first one is inverting amplifier. So there's some analysis, how to analyze, how to get the transfer function, how to get the gain of the inverting amplifier. So basically, it's based on the ideal op-amp model. So that means V minus V plus is the same, the voltage, and there's no current. So I minus I plus is 0. So you can say I minus I plus 0. V minus V plus is equal. Based on this, you can easily derive the transfer function. So this is non-inverting amplifier. This is non-inverting amplifier. The next one is non-inverting amplifier. So you can see this time, can you remember this one? Why called non-inverting? Because you can say invert, when input is V in, here is in the positive side. So, and also the gain is 1 plus RF over R1. So this is also can be analyzed using negative feedback. So I just want to go quickly, and then we so this called gain bandwidth product. This is depends on which kind of op-amp you use. For good op-amp, you have big gain bandwidth product. But for the low quality one, they have low bandwidth gain bandwidth product. And very important circuit is differential amplifier. So you need this one. You can see they want to the output only sensitive to the difference of V1 and V2. But this one you need to remember this formula. But this formula condition is R1 equal R2 and R3 equal RF. So this is the condition. We will show you if this condition not satisfied, what we can get. We also have some integral and differential circuit and either configuration. This is similar as the inverting or non-inverting amplifier. It's like inverting, like they have minus, right? From minus side. So this is the instrumentation amplifier. I will discuss with you very soon with the detailed analysis. And later I will show you how to use multi-sim. Maybe Jeff will give you step by step how to construct. But I just show you how to build this instrumentation amplifier, because for your assignment 2, every group should build instrumentation amplifier. This time I'm asking you to use both. Maybe just at least use 3 op-amp to build the instrumentation amplifier. You cannot directly pick up an instrumentation amplifier to implement. Now we do the tutorial question. Sorry, for this kind of questions. For this one, can you tell me what's the circuit name? Actually, it's an inverter amplifier or
yes.
Yeah, it's inverting amplifier. So can you get the gain? What's the gain for this one? It's minus or positive?
It's inverting, so negative.
Yeah, so it's a negative 2.5.
Yeah.
Yeah, it's 25 divided by 10, right? And then if Vi equals to 0.5, so what's Vo? It's Vi times, so input times minus 2.5, right? So in that case, it's around 1.25. We look at what we can get. So sorry, it's minus 1.25, right? The gain is negative 2.5. It's 25 over 10. So it's like the V out is so it's V in is 0.5 times the gain. so it's minus 1.25. So for this one, they ask also they ask the current, right? The current, if the current of the 10k ohm. So how to calculate the current here? So how to calculate the current? Because what's the voltage for here? Minus equals to to the plus, right? So in that case, the voltage is here is 0, right? So in that case, you can easily calculate the current. How to calculate? It's VI divided by 10k, right? So VI is 0.5, so divided by 10 is 0.05 milliamp. So it's like 50 microamp, right? So why we can minus 0? Because here V minus equals to V plus, and V plus is 0, right? So in that case, here is 0. So you have Vi here, V0 here. So Vi is 0.5 minus 0 divided by 10k. So 10k, right? And then you get 50 times 10 power minus 6 amp. So it's 50 microamp. Maybe I use directly use the. So for this one, can we do a quick survey? So first you need to know what's the name of the circuit, and then you can calculate again, and then you can calculate the voltage output. I think it is great. So 70% students select the right answer. So I'm very happy. I think like you know the op-amp circuit. At least this is the very typical inverting amplifier. So I think it's a wonderful result. So that's great. Sharing the share the result. So we are really good. So we see another one. We continue. So for this one, what's Ix? Can you calculate the current? So how to, this one is still inverting amplifier, right? So in that case, what's the gain? Gain is -5. In that case, what's VO? And what's the, so the VO is -5, right? Because this gain is -5, so VO is -5. And the current, and the voltage of this port is 0, right? In that case, the current should be from 0 to negative 5 volts, because this goes down, the voltage will drop, go this way. So in that IX should be positive. But what's the value? Value is 5 divided by 10. 10K is 0.5 milliamp. So most students get the right result. That's great. So and also we have some other questions for this one. Do you know what's the name of this circuit?
Non-inverting?
Yeah, non-inverting amplifier. So what's the gain of this non-inverting amplifier? It's 1 plus RF over R1, right? So in that case, what's the gain? Is around 1.25. Is 2K over 8K, right? So in that case, what's the voltage of output? So it's 1.25 times 0.4, right? 1.25 times 0.4, and then you get 0.5. And then you can calculate the current. Current is like from 0.5 volts divided by 5 kilo ohm, and then you get 0.1 milliamp. And then that's the result. We also have this one, a little bit complex one, but it's not hard, right? So this one is again, is this input, is non-inverting or inverting amplifier. It's also a non-inverting amplifier. So in that case, the gain is 1 plus 5 divided by 2, right? So we get the gain. So it's around the 3.5, right? Because 2 divided by 2 is 2.5. You have 1 plus is 3.5. And then you want to get the voltage here. So you can use voltage divider. Why we can directly use voltage divider? Because here in the input, the current is 0. So there's no current here. So in that case, the voltage drop is all from here to here. So in that case, you can just voltage divider. So in that case, this point is 3 times 8 divided by 4 plus 8. So this is the voltage here. And then you times the 3.5, you get VO. We look at. So first is 3.5 is the gain, and then we can calculate the voltage divider, and we get this is 3 times this 8 volt, 8 over 8 plus 4 is 2 volts. In that case, this is the result. So if you have difficulties, you still need to review this part. So I will go to Canvas again, and we look at today's lecture. And this is for last week. So for today, before we need to go to pre-work. So have you read today this week's pre-work? So basically, we have a video.
In this video, we will review
It's
the
for
basics
EEG.
of the electroencephalograph.
So EEG, you need to understand how to how to use a international 1020 system, and you need to understand what the ECG stands for, EEG stands for, and some basic idea, because some group they are doing EEG related project. In that case, you need to pay more attention for this part. So today, actually, we want to develop differential amplifier. Differential amplifier, because like uh, for basically for the ECG, for ECG or EEG, especially for EEG, because the signal is very weak, and we always there's some disturbance to get rid to reject the disturbance. Normally, we need to use a differential amplifier, and with a very high CMRR called common mode rejection ratio. So we need to reject the common part, and then get rid only we sensitive with the different part, the difference part. That's just like the differential amplifier. So in that case, how to get that? We normally we use a very powerful instrumentation amplifier. I will introduce later, very soon. So, but here we want to see what's the differential amplifier. So this is differential amplifier. For ideal differential amplifier, they only sensitive with the difference. So for example, you have a two signal. You can see this two signal is very complex, right? But they have a common part. So the common part, if they put the two in these 2 points, the output should be 0. This is the difference. So we want to detect the difference. So if it's a good differential amplifier, the amplifier should be very sensitive to the difference, insensitive to the common part. So in that case, how to define this, the differential amplifier is good or not? We use a common mode rejection ratio. Actually, we can use like the differential gain AD. So differential gain, we want to it is bigger, right? But for the this also how for the common mode gain. So if the common part, I want the gain be 0 or very big. For the common mode, we want the gain is 0. So in that case, if it's really 0, your AD over AC is a common mode gain, should be infinite. So in that case, the best differential amplifier should have a CMRR is infinite. So for the normal, like if you build a normal, you use op amp, because the resistor things is separate, and they have a tolerant, they have error. So in that normally, if you can reach to 60 dB, that is already very good. 60 dB is around what's the ratio? If 60 dB, do you know how to transfer to ratio? Actually, 20 dB is a 10 power of is a 10, and if 60 dB is 60 divided by 20 is 3, so 10 off of 3, so it's 1,000. But like for if you purchase a instrumentation amplifier, so this can reach to 120 dB or even more. So 120 dB is around 10.6. That means like this kind of differential amplifier is 10 times of 6 sensitive than difference for difference than for the common mode part. So that's the ideal one is like this. We want to just see the difference. It's just like this is a very simple explanation. Like this one, you can see when you input these two, you get out should be the difference of these two figures. So you can see for this small house, there's a window. This have window, this have a window, but this one doesn't have. And then we can also this have a one stone, two stone. This one only have one stone. So you can see if we go ahead.
To quote-unquote signals through a differential amplifier, and the output would look like this. this example is a good way of thinking about EEG signals as something that is not absolute, but rather the difference between two inputs.
Yeah, they want to see the difference between two inputs. So it's a relative signal. So in that case, this is EEG. I'm not sure you read this one. It's lots of montage, so you can understand, and also alpha, beta, gamma, uh, and also delta, theta wave. So I have a very simple multiple choice question. There's two multiple choice. We do it quickly. So the first one. So the voltage range of electrodes of EEG is around A from 10 to 100 microvolts. 2 is 0 to 5 microvolts. C is from 1 to 5. D is from 12 to 20. So it's very good. So the first answer is correct. So it's normally EEG is around from 10 to 100 microvolts. So C is for ECG. So ECG is from 1 to 5 volts, millivolts. Others are not right. So how about the next question? The next one, the effects of EEG waves. So it's mainly for the frequency related question. So we relaunch. So the lowest frequency of EEG wave is gamma wave. The lowest frequency EEG wave is delta wave. The frequency of alpha wave is lower than the delta wave. The frequency of alpha wave is around 0 to 4 volts, 4 hertz. So great. So the second one is correct. So normally it's like I'll show you. So the uh, beta. So first is the delta. Delta is the lowest frequency. It's when you deep sleep. It's 0 to 4 volts hertz. But and the next is theta. Theta is around is during sleep. It's from 4 to 8. So normally if your brain move very slow, that means you are in the sleep state. And if alpha is like light sleep, very light sleep, it's 8 to 13 hertz. When you wakefulness is wakefulness is 13 to 35 frequency hertz. So this is for the ECG for EEG uh, for the EEG, and also we have reading material. So this is the EEG artifacts. So there's lots of artifacts. When you use EEG, you need to be careful. We sometimes even use AR model to get rid of the disturbance, the noise. So I wish you to read this part as well. And also we have a research paper. So neural imaging technique, they have a EEG and MEG, and also they have a MIR, and they have a different kind of. Some is good for some have limitation, some had trade-off between temporal and spectral resolution. So EEG is good for temporal recording, but you have other kind of sensors machine. So you need to read this one. It's a very good research paper. And for your assignment one, you maybe need to read lots of papers like that. And also some EEG knowledge, include the frequency we just discussed. So I think like we maybe concentrate on the, you know our structure like for each week. So now we start to look at technical part, like we go to lecture here. So basically we have an instrumentation amplifier. I will be very quick to discuss instrumentation amplifier, but this one is a very important one because you will be required to build instrumentation amplifier, use 3 op-amp in the assignment 2. So I hope you can try to understand with me. If you have any problem, any questions, just stop me. We can discuss. And if we still have time, I will discuss about filter design. Filter design is also quite important. I will show you why we need to do this, because you have see your assignment 2. In your assignment 2, you need to design ECG recorder or ECG circuit. So in that case, first you need to use instrumentation amplifier, build a gain as 10. So this part, I hope today you can do it. So you can use multi-sim to build instrumentation amplifier. So use 3 op-amp with gain is 10. So this one you need to think about. And then if I have time, I will discuss with you about high-pass filter. So maybe high-pass is this why we need high-pass, because we have some DC component in the signal. If we gain to 100, this will auto range. So in that case, we get rid of DC component. So in that case, we design a high-pass filter. Today I will discuss high-pass filter and low-pass filter design if I have time. And then we build another amplifier. This one, maybe you no need to use instrumentation amplifier. Maybe you just use a differential amplifier, use op-amp to build one. And then you design low-pass filter with 150 Hertz low-pass filter. And then you oscilloscope to observe this one. But because for this semester, we only do simulation, and you no need to go to the lab to do all of the implementation, use real components. But we still ask you to, because if you read the new requirement of assignment 2, so you need to list all the components you will use. And then this one, if you build this one very well, it's very easily to transfer PCB, and then you can print the PCB and purchase. They will soldering all of the things automatically for you. But of course, you can try yourself to solder all the components, because all components is already give the very exact types of and property and features, so you can easily purchase or do simulation. So that's why I want to discuss with you about today's lecture. Today, one is very important, instrumentation amplifier. Second is filter. So it's very important. So I quickly do it. Um, maybe I still use so we first instrumentation amplifier. So instrumentation amplifier, you can just simply treat it as a super op amp. So this op amp is like a very high common mode rejection ratio. So that's I mentioned before. So so it's a closed loop gain block. So it's a very powerful instrumentation, powerful amplifier, differential amplifier. So very good for measure very low level voltage. So if you want to build a EEG or ECG and EMG, you'd better use instrumentation amplifier circuit. So for the IPM, they have some disadvantage. So number one is the input gain is not higher enough, and also input impedance is not big enough, and also they have some imbalance because for the resistance. So these kind of things you cannot avoid because they use uh, separate elements to build the circuit. So you are not using the accumulated circuit. So it's like we need to put them together and then build the super uh, instrumentation amplifier op amp, and so they can be very low signal, like you can see this is especially very useful for this kind of some before, if very a long time ago, they used a bridge circuit to measure very weak signal. But now if you have a instrumentation amplifier, and then you can do it better. So also you can see like because the input impedance is very big, so the current is very low. So in that cannot influence too much about the original signal. So this one very important application is EEG monitor, so medical instrumentation. So we that's why we select instrumentation amplifier to do the first stage amplification. There's other applications for gain control, but for what I mean instrumentation amplifier do, actually they have high input impedance and very easy of gain adjustment. So you can just only tune a resistor value, and then you can change the gain. So actually we will show you later how to read a data sheet of a component. In the data sheet of instrumentation amplifier, you can find the way how to change the gain. So you know, like in this study, in this assignment 2, actually I ask you to build the first instrumentation amplifier with the gain of 10. So can you find the corresponding resistor value to do that? So for the instrumentation amplifier, you can use a single op-amp differential amplifier. This is the amplifier we discussed, but this one is accumulated together, make the resistor is value is very accurate. It's like you remember this condition that you can derive the differential amplifier transfer function. And also you have two op-amp configuration. We will show you later. And the most important one is the three op-amp configuration. For your assignment 2, you can select, I think, at least two op-amp or three op-amp configuration. So one op-amp configuration is not recommended, but you can still use it. So common mode rejection. So I already explained in the example. So we need to reject the common signal. Normally, the common signal is noise signal, so it's all is like a common uh, DC component. So we need to get rid of them. We mainly want to the differential signal. So the difference of the signal be sensitive, be amplified. CMR is the ratio of common mode input and the differential mode input, which produce the same output. So I will show you the formula. So for the instrumentation of the high quality one, CMR can reach to 80 to 120. So 120 I already calculated is around 10.6 ratio. Now this is very important formula. So this is the most important part for today's lecture. Before, if we have final exam, we normally have several equations, several problems, questions related with the CMRR. So in this assignment 2, we also ask you, when you build your circuit, you need to calculate or you need to measure the common mode rejection ratio of your first stage of instrumentation amplifier. So this is I think I will discuss with you later. So you need to implement. So first, in that case, how to calculate the common mode gain. So common mode gain, you can see is VOC. That means common mode output divided by common mode input. They get AC. So if back to here, so for example, for here, if we connect both input and output, minus input, positive input together, you can connect them together and then give a voltage input. For example, you can give 1,000 or 10,000 volt, but this connect together. Theoretically, you want the output is 0, right? Even the input is very high voltage, but your output, because it's commonly the same, they are same, your output should be 0, but you cannot get it is 0. But how to measure it is like if you have output, this is called common mode output. The common mode output divided by the common mode input. Common mode, for example, you input is 10,000 voltage, 10,000 volt. In that case, is if output is 5, it's 5 divided by 10,000. So it's very small, but it still have value. So this is common mode gain. You also have differential mode gain. That means if you have a difference input, for example, this is minus input, minus 1, this is a 0, or this is a minus 1, this is a positive 1, and then your output value normally have very big value, and then this is a differential mode gain. So you use differential mode gain divided by common mode gain, you get CMRR. So you look at the formula. So here is the formula. So in that case, differential mode gain is VOD, differential mode output, and divided by differential mode input. So this one I already explained, so you can get AC and AD. So the CMRR is common mode rejection ratio. It's just like the ratio of the differential gain to the common mode gain. So it's this one. We normally want to the CMRR is the bigger the better. So for the very good instrumentation amplifier, it reached to 10 power 6. That's quite big. So that means AD over AC is 10 power 6. So if you can design your circuit, but unfortunately this semester you cannot measure it because you cannot implement it. But you can still simulate. Based on simulation, you can calculate the CMRR because the multi-sim is quite good. So they also consider some real issue. So you can do the simulation. And also called CMR, this is called common mode rejection. They did not put a ratio. So they use log, 20 log 10. This is called a dB, right? You already heard we use about dB, right? So in that case, for example, I said if I said it's 100 dB, if a CMR is 100 dB, can you transfer to CMRR, common mode rejection ratio? If it's 100 divided by 20, divided by 20 is 5. So if log 10 CMR in that case is 10 power 5, right? So it's if 100 dB is 10 power 5. So you should remember this uh, this slide. This is a CMR. It's very important one. So some other properties like they are all very wonderful properties. They have very small offset drift and also some very small, very low noise and also very low nonlinearity. So this is our all uh, advantage of use instrumentation amplifier. So this is a one op-amp, one op-amp instrumentation amplifier. So actually, you can see this is what's the circuit name. Actually, it's a differential amplifier, right? So it's differential amplifier. Can you calculate what's the gain of this differential amplifier? If it is 100, 100, so what's the gain? If if the voltage value, if the resistance value is very accurate, and then the gain is 1, right? So the gain is 1. This differential gain is 1. What's the common mode gain? What's the common mode gain? If I connect V1 and V2 together, what's the output? Ideally, it should be 0. No matter your input, how big it is, should be 0. But this is under the condition R1 equal R3, R2 equal R4. I will give you, in the future, I will derive that if if R1 and R2, R1 and R3 is not equal, R2 and R4 is not equal, but their difference is very small, I will derive what's the CMRR. So I have the formula. Actually, you can search in the web as well. So here, if you if the result, if this one is not satisfied, you still can derive the differential gain. So I give you this one as homework. Can you derive the differential gain? Is this? It's not that simple, right? It's not something like this. This is under the R1 equal R3, R2 equal R4, right? This you can get the V out is like that. So maybe you can select if R1 equals to R3, R1 equal to R3, and R2 equal R4. You can simplify this. You can get something like that. So this is without the condition. R1 is not equal to R3. So in that case, you can get ID like this. AC, you can get like this. So this is for example, if they are equal, for example, if R1 equal R3, R1 equal R3, R2 equal R4, that means AC should be, that means R1 times R4 equals R2 times R3. So in that case, RC should be 0, right? So this ideal case, we want this one be 0. And then this is only have AD, so AC is 0. And then what's the CMRR? So it's this one divided by this one. If this one 0, and the CMRR will be infinite. So that's what we want. So in that case, CMRR, the formula is like this. For example, you can see if R1 equal R3, R2 equal R4, then the denominator for this one will be 0. And then this will be infinite. So in that case, the CMRR should be infinite. That's what we want. But it is not possible in the real situation. R1 times R4 minus R2 times R3 is never be 0. It's very unfortunate. And especially when the temperature changing. So this one is keep changing. So it's cannot guarantee it always be 0. So this is resistance related. Actually, your op-amp itself is also a amplifier, right? It's also a differential amplifier. It also have CMRR. So if I ask you what's the overall CMRR, and then you have another formula. So here. So this is the formula, overall formula. So it's the overall CMR. You also consider about op-amp CMR and also the component CMR. This is an example to calculate. So for example, if you purchase op-amp, the op-amp have the CMR is 70 dB. So CMR is 70 dB. But when you purchase 0.1% tolerance resistor, so this is already very high quality resistor. When you build the circuit, and then your total CMR dropped from 70 dB to 66 dB. So that means like the overall is dropped. But if you build them in the assembly circuit, and then it will be better. So that means you can purchase one op-amp instrumentation amplifier. So this is CMR for single op-amp. So this one is a 3 op-amp configuration. So this one, the trans function we discussed. So this part is a differential amplifier. If you want to input increase the input impedance, and then you put another 2. This like you can see the gain. What's the gain for this one? Is 1, right? This is like a buffer, right? So in that case, V1 is equals to here, V2 equals to here, but the input impedance is increased a lot. Because you can see this is a ideal op-amp. So in that case, the V2 here equals to the V minus. So in that case, easily see V2 equals here, V1 similarly equals to here. So they didn't change anything, but the input impedance increased greatly. So that's the 3 op-amp circuit. Of course, you can use the value from put a different value here. You can also change the gain. So the 3 op-amp circuit has the matched high impedance input, and therefore a minimal effect on the overall CMR. So it's a very good one. And so this is give you the how to derive the CMR as well for 3 op-amp circuit. So it's CMR total is CMR for the B for this part, and times the AD, the DA, the first stage. So this is the first stage again for this one, because you have some here is not the buffer. So because here have value R5, RG, and R6. So this is the differential gain for the stage A, and stage B is like this. This is a, can you see this is means ideal case. You can see this is ideal case. R1 equal R3, R2 equal R4, R5 equal R6. You can get ideal case. But the overall CMR is like the total CMR, because CMRB we already developed for the single op-amp differential amplifier. We already derived CMR B, right? And then you only need to times the differential gain of the first stage, and then you can get the overall CMRR. So in your assignment 2, you can look at this one. So I think this is the 2 things I want to emphasize. Of course, you have a 2 op-amp instrumentation amplifier. So this one used to be the final exam questions. You need to derive the transfer function. So this is like a little bit challenging. If you are very good on the op-amp circuit, and then you can derive the transfer function. So the transfer function we will discuss in the future, but for the assignment you maybe not need to use. There's some tutorial question. I think we don't have enough time. If I have time, later I will go back to, but I already put this question to you, and you can try. But this is very interesting and very practical questions. So this is like, for example, if there's a instrumentation amplifier, normally your CMR is the AD divided by AC. It's a common mode, I mean differential mode gain divided by common mode gain. Actually, if you not match very well, even your common mode input will generate a differential mode output. That means, for example, your resistance in the two port is imbalanced here. So this one is imbalanced. It's RU is unbalanced voltage. I will show you use multi-sim to show if you have unbalanced, for example, unbalanced structure. So here is the instrumentation amplifier. Before we start the next topic, so we don't have enough time to do the things, but I show you how to like multi-sim. Actually, Jeffrey maybe or Kari, maybe Jeffrey will give a very detailed explanation about how to use multi-sim, because multi-sim is quite important. And like previous week, we already asked you to install. I'm not sure how many students installed the multi-sim, but if you not install multi-sim, you cannot do assignment 2. So assignment 2 is totally depends on the multi-sim. So in that case, I show you what's the first stage of your assignment. You need to do is 3 op-amp. So this is 3 op-amp. 3 op-amp instrumentation amplifier. So you need to build something like this. If we because you can see the two input signal, they are exactly the same, right? Can you guess what the output should be? If the input is exactly the same, what the output should be? Because this one differential gain. I mean the common mode gain, if it's very because common mode gain normally is very small for this one, because this one 3 op-amp circuit. So in that case, the output nearly 0. So in that case, we do the simulation. You can do the simulation. So very close to 0, but have some value, right? Still have some value, but actually it's you can nearly it's very very small. But for example, there's a DC difference. But if I change this one to another value, for example, I give a phase. For example, I give a 1 degree. One degree is a little bit. I put a 0.1 degree. Okay, I stop. Jeffrey will teach you how to use multi-sim step by step. So here you can see this one is increased a little bit. I think maybe this is like oscilloscope here. Oscilloscope, because this semester you cannot use real oscilloscope if you select online lab, but you can. This one is exactly similar. You can see you have 2 channels. Channel 1, I use channel A, so this is channel A. So I can tune the scale, so I can change the scale. You can see if I change the scale, and then this input is in. I can also change the time scale as well. Time scale as well. So in that case, it have some value. But if I make it a little bit bigger, the change you will observe the change. If I change this one to 1 degree, normally they will. I put as 5 degree difference, and if I do the simulation, this have some. sorry, I put the distortion phase. Okay. If I put this magnitude change to, for example, 1.5, and then this one will have mean the differential input will be big. So you can see it's very big. It's a very big difference, and then you need to use how to use the oscilloscope. So you use channel A. So first you need to tune the Y amplitude, and also you need to change time scale as well. Time scale, and also you change the. So you can measure the output because of input is different. So you can get because the only sensitive with the difference, and you can measure the things, but you need to think about how to measure the CMR for this one. I leave you to home. So, but this one I still change back. I want to show you what's the. I still change back to the. They are exactly the same. If they are exactly the same, what's the output? So they're nearly zero, right? The output nearly zero. But if I put unbalanced input impedance, if I put this in, so there's only 100 ohm. So this is quite small, but this one, because you always cannot avoid something like this 100 ohm difference, and then when you simulate, so your differences will you have some bigger difference than before. If I without this one will be smaller. So this is because the time is very tight. So maybe I start to discuss about how to use multi-sim. So this multi-sim, actually there's some example you can find use multi-sim. There's lots of example you can search, find example. This one didn't. So today maybe we don't have time to finish the filter design, but I will discuss with you next week because next week you need to maybe submit assignment 1. So it's I think it's 31st. I mean, maybe I show you where's. So mainly you look at here, study guide here, the second page. You can see all assignment 1 is 31st of August. We need to submit. So it's next Monday. If you I think you concentrate on this one, the assignment 1 first, and then you can think about assignment 2 as well. Yeah. So this is something I want to emphasize. And next week, I will discuss with you about filter design. So analog filter design, this is a very important part. I hope you can read something about filter design. So I will show you how to use MATLAB to design a filter as well. This is the things I don't have time to cover. Maybe Jeffy. Hi, Jeffy. Hello. Hi, can you hear me, student?
Yeah, we can hear you.
Okay. In that case, maybe Jeffy haven't come yet. In that case, I will give you some very basic introduction about how to use multi-sim. So this one is how to find some example. For example, you want to do the amplifier. So you have several amplifier circuit you can search. Hi, Jeffy. Hi. Can you? I cannot hear you. Yeah. So they have have several example you can select. For example, amplitude modular. They have a different. Maybe you can search the one you really want, so, and even you can search in the website. They have some people already developed some circuit. So this is a fun example, and they have lots of you can digital and analysis and getting start. There's several examples you can getting start with the multi-sim. So you can see. Hi, Jeffy. And then you need to familiar with all the how to change the component. For example, this one, if you want to change component, you can replace component, and then they give you lots of components. For example, this op-amp, right? You can use a different op-amp. For example, this one or some other op-amp, and also you have lots of detailed report, some material to describe describe this kind of things, and also so you can see this change to the different op-amp, and also you have lots of like this one is also some. This is a voltage. Sorry, it's a source. You can input. You want to some different power. This is power you want to use, and you also have lots of. This is a components. You have a resistor value. So for example, you can change different for different resistor value, different type of resistor value, resistance value, and you can put switch, a lot of things. So that's good thing is for multi-sim. They include lots of, I mean, what's the? Hi, Jeffy. I cannot hear you. Any other people can hear you? Maybe I change you as
No.
okay.
Yeah, we can't hear him.
Cannot hear him, right? Can you, if you cannot hear him, I give you Jeffy. I give you the.
Oh, can you hear me now?
Yeah, I can hear
Yeah.
you.
Fix it.
Okay. How about other people? Can you hear Jeffy?
Yeah.
Okay.
Yeah.
Hi, Jeffy. I should I put you as a maybe a call maybe a host?
Yeah, cool.
Yeah, you are the
Yes.
host now, and maybe
Yeah, I'll share my
the
screen.
voice may be more clear. Yeah, you can share your screen. I just give a very quick explanation. I think like you give them very basic introduction about multi-sim.
Okay.
Yeah,
Yeah.
as fast
So
as you can.
okay. So once you open